So this next step is arguably one of the most important parts that we've looked at so far, because it's really going to discuss how chemists determine what a chemical is. So imagine, for example, that one of your grandparents hands you a chemical and they're like, what is this? And is this safe to drink or whatever? And you're like, oh man, don't do that. So you've got to find out what it is, and you don't want to drink it and you don't want to smell it because there's a lot of really deadly things out there. So what a chemist will usually do is they'll take the chemical and they'll send a little bit of it off for analysis. And the analysis, the goal is to get what's called the molecular formula. The molecular formula is kind of the holy grail of this kind of stuff. And if you have the molecular formula, then you can figure out what it is. But in the process of determining the molecular formula, a lot of times the chemist will have to go through what's called the empirical formula. And the empirical formula is the smallest whole number ratio of atoms in the formula. So on the little table there in the middle right, you can see the comparison of molecular formula versus empirical formula. Now, it's really important in the empirical formula to have the smallest whole number ratio. Chemists don't do fractions generally, and we're certainly not doing fractions in this section. So H2O, for example, which is water, the empirical formula, the smallest whole number ratio of atoms would also be H2O. Now, yes, you could have an empirical formula of H1O.5, 1/2, but don't do fractions in my class, especially not right now. So H2O is the empirical and the molecular formula. So let's look at some more exciting examples. Glucose is a type of sugar. The molecular formula is C6H12O6. Well, the empirical formula, the smallest whole number ratio of atoms, if you divide the 6, the 12, and the 6 in the formula, divide them all by 6, you get C1H2O1, or CH2O is the empirical formula. And again, don't go to fractions, smallest whole number ratios. Likewise, hydrogen peroxide, H2O2 is HO, butane C4H10, which is used in cigarette lighters, by the way, would be C2H5, etc., etc. If a chemist has the empirical formula, they can use a mass spectrometer, which we talked about in chapter 2, to find the molar mass of the compound. And between the molar mass of the compound and the empirical formula, you can find the desired molecular formula. So we're going to explore this whole pattern, this pathway, in this section, and I'll show you how chemists do it. One of the types of analysis that chemists will send away these unknown chemicals for is called a percent composition. And there's various ways to do a percent composition or percentage by mass analysis. Atomic absorption is one method, but there are several of them. Anyway, you'll end up then with these percentages of the elements in the compound. So in the bottom down there is an example of ethanol. Ethanol has a molecular formula of C2H6O, and you can see that that compound is 52.13% carbon, 13.15% hydrogen, and 34.72% oxygen. Now, eventually, we're going to take those percentages and turn them into empirical formulas, but we should also talk about a little bit about how these compounds came to be. But before we do that, all of your percentages for the elements should be very, very close to, if not equal to, 100%, because these are all the chemicals in the compound. So these percent compositions will tell you what kinds of elements you have. So for example, ethanol has carbon, hydrogen, oxygen, but no nitrogen, no uranium, stuff like that. And it will lead to an empirical formula, but it doesn't lead to that molecular formula. So now first, before we talk about how to get to molecular formula, let's see how percent composition can help us, and also how to calculate what the percent composition should be. This is an example where we have 10 grams of some compound, and it's found to be 2.5 grams hydrogen and 7.5 grams of carbon. We can find the percentage by mass of hydrogen and carbon using this information. And it's probably not too hard, and maybe you can figure out how to do this, but if you can't, no big deal. These percentages, what you want to do is take the grams of the good stuff in the numerator, the top, and divide by the total mass of whatever you're looking at in the bottom, and then multiply by 100%. So for hydrogen, that would be 2.5 grams of hydrogen, the thing we're looking at. We'll divide it by the total mass, which is 10 grams, multiply it by 100%, and this comes out to be 25% hydrogen. So our compound is apparently 25% hydrogen. Now, to find the percent carbon, which is the other thing, there's two ways you could do it. You could take 7.5 grams of carbon, which is how much was found, divide it by by the total 10 grams times 100%, 75%. That's legit. But you could have also found it remembering that all of the element percentages together equal 100%. So 100% minus 25% hydrogen would mean you'd have to have 75% carbon. That's a nice way to check yourself, kind of make sure that you've got the right answers for things. If you know the formula of the compound already, you can also find the percent composition. So as an example of what I mean by this, let's consider water. Good old H2O is going to follow us all the way from Chem 221 through Chem 223. But water, if you remember, we could find the molar mass of water. It's 1 oxygen, which is 16.00 grams per mole, and 2 hydrogens, 2 times 1.01 grams per mole. So the molar mass of water, 18.02 grams per mole. That's to the 100th place, etc., etc. Well, the percent oxygen in water would be the grams of oxygen divided by the total mass times 100%, like we just saw. But in this case, we're going to use the molar mass in the denominator. So 18.02 grams is the mass of 1 mole of water. And in 1 mole of water, as you saw in the formula, there's 1 oxygen, which is 16.00 grams. So 16.00 divided by 18.02, that represents the grams of oxygen divided by the grams of the total mass of water times 100%, 88.79% oxygen. And to find the to find the percent hydrogen, you could do something similar. You would take the mass of the hydrogen. There are 2 hydrogens, which each are 1.01 grams, divided by the total mass times 100, 11.2%, and that's fantastic. However, you would get better sig figs here by going 100% minus the percent oxygen, which is legit too. So instead of 11.2%, you would get 11.21%, which is woohoo! 1 sig fig better. Not a big deal, but either way would be fantastic here, and you get the idea of how this works. So what we've just seen here are 2 methods to find percent by mass. If you know a total mass, like in the last example, you can put that in the bottom, divide, or have in the numerator put whatever mass you're looking for. Or in this case, since we knew the molar mass, we could put that on the bottom and then find the masses of the individual elements, and they should be the same result. This is a question you might see. It says, what is the percent nitrogen in nitrogen monoxide? And MM stands for molar mass. NO is about 30.01 grams per mole. So the nitrogen, there's 1 N in NO. Nitrogen is 14.01 grams per mole. So the percent nitrogen in this case would be 1 nitrogen divided by the molar mass of the whole thing times 100%. Mathematically, that would be 14.01 on top. You would divide it by 30.01 on the bottom, multiplied by 100%. It'll be a little less than 50% because 15 divided by 30 is 50%, and NO is a little less than 14, so it comes out to be 46.68% nitrogen. And there's the better math there on the bottom, but you can kind of estimate. So anyway, no problem. It's just another little trick of the trade if you need to use it. So like we said earlier, the compound's empirical formula is often the first step in determining the identity or the molecular formula of the compound. And you can find the empirical formula from these mass values. If you have the exact masses, you can turn the masses into moles. And then from there, you can take those moles, divide the mole values by the smallest number of moles. That'll give you then whole number ratios. And if necessary, sometimes it is, sometimes it isn't. If you have a fraction, you can multiply the fraction by a whole number to get a whole number ratio of subscripts. So what that means is maybe you'd end up with the first atom being 1 and the second atom being 1.5. Well, that's great, except that you couldn't have an atom which was only 1.5 atoms. Oh, that breaks all the rules of chemistry, which has whole numbers. So you'd multiply both of them by 2. You'd have a 2 to 3 ratio that way instead of a 1 to 1.5 ratio. I'll show examples of how this means here in a second. Let's look at an example here. We have 1.71 grams of carbon and 0.287 grams of hydrogen. Let's find the empirical formula of this compound. Okay, no problem. We're going to turn the grams of C into moles of C. We're going to turn the grams of H into moles of H, and we'll compare the C and the H. So here's the math. 1.71 grams of carbon will divide by 12.01 grams per mole for carbon. You can see there the grams of C cancel out. We've got 0.142 moles of carbon. We're going to do the same thing here for hydrogen. 0.287 grams of hydrogen divided by 1.01 grams per mole. That gets us 0.284 moles of hydrogen. This is kind of a ratio. It's like a ratio, you could think of it as C 0.142, H 0.284, but those are anything but whole numbers, which is what we need in chemistry for formulas. So we'll take those 0.142 and the 0.284, we'll divide it by the smaller number, and 0.142 is smaller than 0.284, so we'll divide both of the moles by 0.142. C comes out to be 1 then, 0.142 divided by 0.142 is 1, and 0.284 divided by 0.142 in your calculator is a 2-to-1 ratio. So that means we have 1 carbon, 2 hydrogens. Our empirical formula here, CH2. So again, this is not the molecular formula, but this is the first step that usually scientists have to do in order to find that desired molecular formula. So in this particular case, our empirical formula, our smallest whole number ratio of atoms, CH2. Here's another example where we have chlorine and oxygen now instead of carbon and hydrogen. Same thing, let's find the empirical formula. So again, grams to moles, we'll compare the moles, we'll divide the moles by the smaller moles to get the empirical formula. In this case, 5.31 divided by, I believe it's 35.45 grams per mole of chlorine, you end up with 0.150 moles of Cl. Try this on your own, make sure this is cool. And the same thing for oxygen, 8.40 divided by 16.00 grams per mole, you get 0.525 moles of oxygen. So those are the moles now of Cl and oxygen based on those mass values. And again, this is a kind of a formula. It would be Cl 0.150, O 0.525. But wow, is that an ugly formula? You need whole numbers for formulas. So we're going to divide both of those numbers by 0.150. If you do that, Cl 0.150 divided by 0.150 comes out to be Cl1, and oxygen 0.525 divided by 0.150 comes out to be 3.5. So this is better. I mean, we've got whole numbers now for chlorine, but oxygen 3.5, gotta get rid of that, gotta have whole numbers. So we'll multiply both of those through by 2. That means it's going to be not 1 to 3.5, but 2 to 7. So the empirical formula here, Cl2O7. So you can see here that after we divided both of the numbers by the smaller moles, we still ended up with a fraction or a decimal, but 3.5 times 2 is 7. So 2 to 7 is a better empirical formula than 1 to 3.5, empirical formula Cl2O7. Now in Chem 221, you're not going to see crazy ratios. You might see 0.5, all right, and if you multiply 0.5 by 2, you'll get whole numbers. In the real world, though, you might get 3.25, like 3 1/4. And does that mean you have an impurity and you should round down to 3? Or does it mean you should literally then multiply through by 4 or something to get whole numbers? And this is a difficult decision sometimes, but it's one that chemists face. Nothing you can't handle. But again, in our classes, the ratios will be pretty simple. This is a general plan for what we just did and how you go from mass percentages or mass values, I guess I should say, into an empirical formula. So we took the grams of Cl and O, turned them both into moles by dividing by the molar mass. We then compared those moles together, and it turned out it was 3.5 moles of oxygen for every 1 mole of Cl. But we can't leave that stand. We have to have whole numbers, so we multiply them both through by 2 to get 7 to 2 ratio, which means the empirical formula here, Cl2O7. Now, the last examples have had actual masses involved. So we had actual gram amounts of, say, carbon and hydrogen or chlorine and oxygen, and that's cool. But you can do the same kind of process with percent composition values. So in this example now, we're going to have percentages instead of grams, but it's amazingly similar in how you make this happen. First of all, if you have percentages, what I would do is assume you have 100 grams total of your compound. So that way your percentages become grams explicitly. And I'll show you what this means here in a little bit. But once you have the grams of the elements, you can turn grams to moles, divide the mole values by the smaller moles, and if necessary, multiply them all through by an integer to get whole number of subscripts. So in this example, we've got some kind of compound that pops out here. It's 27.29% carbon and 72.71% oxygen. We can use this information to calculate the empirical formula of this gas. So again, what we're going to do is we're going to take these percentages, assume 100 grams total. That means 27.29 grams of C and 72.71 grams of O. We'll turn the grams into moles. We'll compare them, see if we can find a smallest whole number ratio of atoms. So what I would do is I would assume 100 grams total, so those percentages literally become grams. So 27.29% carbon became 27.29 grams of C, and 72.71% oxygen became 72.71 grams of O. You can use different numbers. Some people like using 1, and that's fine. You'd have 0.2729 grams of C and 0.7271 grams of O, and that's fine. You can use any number you want, but I just use 100 grams because I'm lazy and I don't want to think about it, but you use whatever you want. The next step though, turn the grams into moles. So using my values, I ended up with 2.272 moles of C, 4.544 moles of O. And again, I got those molar masses from the periodic table, no big surprise. We'll then take both of those mole numbers, we'll divide them by the smaller number, which here is 2.272. So if you do that, 2.272 divided by itself is 1. 4.544 divided by 2.272 is almost exactly 2. That means 1 carbon every 2 oxygens. Empirical formula here, CO2. So again, very similar to what we just did, just assume percentages. You want to turn them into grams. I would assume 100 grams, grams to moles, compare the moles, empirical formula, good to go.